All right, in this section, we're going to be covering graphs of polynomials. So let's go ahead and start with what is a polynomial, right? So a polynomial function is a mathematical expression when we graph it, we end up with a graph that's smooth and continuous. So by smooth, I mean that it has no sharp points. It just runs smoothly. And continuous means that it doesn't have any empty spaces. So if I were to graph something, it would just look like a little snake, right? It's smooth and continuous. It just keeps on going. Now, when we're talking about polynomials, there's going to be a very important thing we're going to be seeing over and over, which is the word degree. So let me just tell you what that means. So when I give you a polynomial function, the degree of the polynomial function is going to end up being a number. And that number is going to tell you the maximum number of real zeros or roots or solutions or x-intercepts that the polynomial has. I know I'm freaking you out, right? But these four things, the reason why I included them in here is because they all mean the same thing. Okay, so if throughout the video you hear me saying the word solutions, it's the same thing as if I was saying x-intercepts or roots or zeros. All of these mean the same thing. Okay, now how in the world do I find the degree of a polynomial? There's two different ways. So I make sure to put them here and make sure you have them on your notes. When I ask you for the degree of a polynomial, it depends if the polynomial is in standard form or factored form. So I'm going to go over both of them. If your polynomial is in standard form, meaning that it has no parentheses, your degree is simply going to be the highest exponent. Just look at all the exponents. The highest exponent is going to be your degree. Now, if your polynomial is in factored form, meaning that there's parentheses, in order to find the degree, we're going to have to find the sum of the exponents. So that means we're going to have to go through and add all of the exponents, okay? So that's what you're going to do. It's pretty simple. That's how you're going to find the degree. And like I mentioned before, the degree is important because it tells you what's the maximum number of x-intercepts you can have, or roots, right? It all means the same thing. Now, something else we're going to be talking about is the maximum number of turning points. So we're going to be talking about it later on, but for right now, just write down the formula. The maximum number of turning points is always going to be found by subtracting 1 from your degree. So for example, if a polynomial has a degree of 10, it means that it has a maximum number of turning points of 9, right? Because all you do is just subtract 1. All right, something else that we have to talk about for polynomial functions, since we're going to be graphing them today, there's this thing that's called end behavior. The end behavior of a polynomial function just means, how does the graph look like? Like, does it go all the way up on the right side? Does it go down on the left side? That's what we call end behavior. In order to determine the end behavior of a polynomial function, we're going to use this little thing called the leading coefficient test. It's a test that we're going to use, and it's going to tell us whether the function goes up or down. Now, the leading coefficient test, we're going to be using it, but in order to use it, we have to know two things. We're going to look at the leading coefficient, and we're going to be looking at the degree of the polynomial. Okay, and don't worry, we're going to do an example in just a bit. So the leading coefficient test is right here on this next slide. In your notes, right, this should be empty, so make sure you fill it up correctly because this chart is going to be very helpful. So like I mentioned earlier, in order to use the leading coefficient test, we're going to look at two things. We're going to look at the degree of the polynomial. You're going to determine if it's odd or even. And then you're going to look at the leading coefficient, and you're going to check if it's positive or negative. If your polynomial has an odd degree, and by odd, if you don't know, make a little note here. Odd numbers are 1, 3, 5, 7, and such. And your leading coefficient is positive, your graph is going to look like this. It's going to fall to the left side, and it's going to rise to the right. Another way of saying that it's going to go to the negative side on the left side, and on the right, it's going to go up towards the positive side. Now, if your polynomial is odd degree and has a negative leading coefficient, then it's going to be backwards. It's going to rise to the left, and it's going to fall to the right. Okay, so that's one way of saying it. This is another way of saying it. It's going to go to the positive on the left, and it's going to go to the negative on the right. Now, the last two scenarios. If your degree is even, and again, if you don't know what even is, make a little note of it. Even numbers are 2, 4, 6, 8, and so on. And your leading coefficient is positive, that means that your graph is going to go up to the left side. So it's going to rise to the right, and it's also going to rise to the left. So sorry, rise to the left and rise to the right. And again, another way of saying that is goes to the positive on the left and positive to the right. And the very last scenario, if your degree is even and your leading coefficient is negative, then that means it's going to fall to the left and fall to the right. or negative to the left, negative to the right. So these are the 4 scenarios we could have when graphing. Again, make sure you have this written down because it's gonna come very handy when we're graphing polynomials. All right, so let's see if we could come up with an example here. So here's an example of a polynomial, and they're asking us to determine the end behavior. Of course, you could graph this, but I think it would take you longer to actually pull out a calculator and graph it because we could just use the leading coefficient test. So have the chart that we just talked about next to you, and this is what we're going to do. In order to use the chart, we have to know the two things. We have to know the degree and we have to know the leading coefficient. So remember, there is no parentheses here. So this is in standard form. So the degree is the highest number. So the degree right here is the highest exponent, which in this case would be 6. So I'm sorry about this. So make sure you fix this. The degree should be 6 because that's the highest exponent. And what is 6? Is it odd or even? It's even. So in your chart, go to the degree is even. Now we still have to look at one more thing. We have to look at the leading coefficient. The leading coefficient is the number in front of the highest term. So this right here is the highest term because that's the one with the highest exponent. Leading coefficient is the number in the front. If there's no number, it's an invisible. Okay, that's supposed to be a 1. There you go. So it's an invisible 1. So the leading coefficient is 1, which is positive, right? It doesn't have a negative sign. So just go to your chart. What happens when you have an even degree and a positive leading coefficient? The graph rises to the left and rises to the right. And that's it. That's the end behavior. That's what we were looking for. So if you were to graph this, the graph would start up here and then something would happen here. I'm not sure. But eventually the graph is going to end over here. That's what end behavior means. So it's going to rise to the left and rise to the right. Okay, let's try this one. This one, same thing. Determine the end behavior. By now you should know there's 2 things we have to look for. We have to look for the degree. The degree is the highest exponent, which is 5. And you ask yourself, is it even or odd? It's odd. Now, I also have to look at the leading coefficient. Leading coefficient is the number in the front. Of course, this is the number in the front because that's the highest one, which is 7. I don't care if the 7 is even or odd. I care if it's positive or negative. So I ask myself that's positive. So just look at your chart. What happens when I have an odd degree with a positive leading coefficient? Then the graph falls to the left and rises to the right. Okay, so it would fall this way. Something would happen and eventually it would rise like that. Okay, so I think this is pretty simple, right? Like I said, that little chart that we talked about earlier is going to be your best friend for these types of problems. All right, now here things change a little bit, right? So again, determine the end behavior, have to figure out the degree and the leading coefficient. But like I mentioned earlier, the degree is not 2 because you only grab the highest exponent when the polynomial is in standard form, meaning that there's no parentheses. This one is in factored form. So if you go to your notes from earlier, when we have something in factored form, in order to find the degree, we have to add the exponents. So there's no x out here, so I don't care about the exponent. In this case, I have an exponent of 1 inside and 1 outside. So if you multiply those, I have an exponent of 1 here. Now we're going to have to add. The exponent here is 1, but the exponent outside is 2. So you multiply those, and the exponent overall here is 2, right? Because we multiplied the 1 and the 2. And then we have to add the final exponent here. The exponent inside is 1. The exponent outside is 1. You multiply those. 1 times 1 gives me 1. So the overall degree of this whole polynomial is 1 plus 2 plus 1, which is 2. So the degree of this polynomial is 4, which is even. And now I have to look at the leading coefficient. The leading coefficient is obviously right there. So the leading coefficient is 36, which I'll tell you right now why, but it would be positive. Okay, so that's what we care about. Now, I know you're wondering, where in the world did you get the 36? So let me go ahead and erase this real quick. So in order to find the leading coefficient, like I said, it's right here, but that's only the one on the front. This is also a leading coefficient. And the little 1 here is also a leading coefficient, and so is the 4. So we're going to have to take all of those into consideration. So all we're going to do is 3 times 3, which is 9, times the 1, times the 4. Okay, so if you could help me out here, 9 times 1 times 4, that's how I got the 36. Okay, so going back to the two last problems, I know you're wondering, why did she not do that on the last ones? Because again, there's no parentheses here. So the leading coefficient is simply the number in the front, and the degree is simply the biggest one. But now when you have parentheses like these, we had to add all the exponents to find the degree. And in order to find the leading coefficient, I had to multiply all the leading coefficients in each one of the parentheses. But now we still use the same chart. So what happens when you have an even degree and a positive leading coefficient? The graph rises to the left and rises to the right. So if you need a little picture, it rises there that way, and then it rises that way too. Okay, so I'm hoping that made sense. Like I said, the chart is going to be very helpful. Now, once you determine the end behavior, we can also find the zeros or the x-intercepts or the solutions or the roots. Like I said, all of those things mean the same thing. Don't let it overwhelm you. In order to find the zeros, let's just stick to that. In order to find the zeros of a polynomial, there's two steps. The first thing you have to know is that the polynomial has to be in factored form, meaning it has to have parentheses. Once it's in factored form, you're going to set each factor or each parentheses equal to 0 and solve. So let's go ahead and try one of those problems. So here we have a polynomial, and they're asking us to find all the zeros. Another word for that is it could have said find all the x-intercepts, or it could have said find all the roots. It all means the same thing. Now let me go back to the notes. Step 1, the polynomial has to be in factored form. Is this in factored form? No. How do you know? There's no parentheses. So what we're going to have to do is we're going to have to factor this out. But again, we already know how to do that. In case you don't remember, when you have a polynomial with 4 terms, in order to factor it out, we factor by grouping. So I group these two. I'm not going to go into it. If you need help with this, remember we did have a whole video on factoring. I factor the greatest common factor from those two, which is x squared, leaving me with x plus 2. The greatest common factor of the second group is -4, leaving me with x plus 2. When we do factor by grouping, since those two are the same, I write it once, which is x plus 2. And then in the other parentheses, I write the leftovers, which is x squared minus 4, which is this right here. Again, I'm not going to go into it as much because we already covered factoring for like a whole week. Now from here, you should know that this is a binomial, which is a difference of squares. So every time you have a perfect square minus a perfect square, that can be written as x minus 2 and x plus 2. Okay, so I'm going to go ahead and do that real quick here. So this right here becomes x plus 2. So I know I didn't type that out, but I'll write it down here. And x minus 2. Again, if you don't know what I'm talking about, go back to your notes on factoring. And we learned that when you have a binomial like this one, that is a difference of 2 perfect squares, you can factor it out like this. So we have x plus 2 times x minus 2 coming from this one, so I'm going to get rid of it. But I still have an x plus 2. Now, what do you do? X plus 2's. So that's why I rewrote it like this. We're going to have x plus 2. I'm sorry, the square actually goes here. And then we're going to have an x minus 2. And I'm going to go ahead and erase that right there. Okay, so hopefully you were able to see that. So when they ask you to find all the zeros, you have to make sure your polynomial is super factored out. So if you notice, we did have to factor out by grouping. And then from here, we had to make sure we factored out even more, which was this part could be factored like that. So my final answer would be x plus 2 squared, x minus 2. Now, we're not done yet, but we're almost there. In order to find the zeros, now I just have to get each one of these 2 and set it equal to 0. So if I grab this and I set it equal to 0, I move the 2 to the other side, giving me -2. And then I grab this parenthesis, set it equal to 0. I throw the 2 to the other side, giving me the +2. All right, so that's how you would find your zeros. Again, this one was lengthy, but I wanted to do the hard one with you. There's going to be some polynomials that straight up are going to be factored out. So You might open up the homework, and if you get lucky, you're just going to have this. So you wouldn't have to worry about factoring. You would just get each parenthesis, set it equal to 0, and go to your answers. Okay, but just a word of warning, if your polynomial is not factored out, you are going to have to factor it out first and then set it equal to 0. All right, so now that we know how to find our x-intercepts, because again, that's what we did on the last slide. When you're talking about roots or finding zeros, it's the same thing as finding x-intercepts. Now, once you know how to find your x-intercepts, you could also find the behavior. We already talked about end behavior, which tells you how the graph behaves at the very ends, right? What happens to the left? What happens to the right? But when you have an x-intercept, you could actually determine if the graph is going to touch an x-intercept or cross it. And that's what we're going to be talking about here. So in order to determine a graph's behavior at an x-intercept, we're going to be looking at what we call a multiplicity. Multiplicity is just a fancy word for exponent. Okay, so an exponent is going to tell you the behavior of the graph at an x-intercept. So this is what you have to have on your notes. If a 0 or if an x-intercept has an even multiplicity, and by even again are numbers like 2, 4, 6, 8, then the graph is going to touch and turn the x-axis at that 0 or at that x-intercept. Okay, again, I don't expect this to make sense, so just make sure you have it on your notes. And right now we're going to be doing an example. Now, the opposite of that, if a 0 has an odd multiplicity, and again, by odd, I mean 1, 3, 5, 7, then the graph is going to cross the x-axis at that 0. Okay, and this is what I mean. Let me draw a picture here. So, if an x-intercept is right here, if the graph has an, or if the function has an even multiplicity, it's going to touch and turn. It means that the graph is going to touch the x-intercept, but it's going to turn back. This is what I mean by touch and turn. Now, by crossing, I mean that we have something like this. If we have the same x-intercept, but if it has an odd multiplicity, that means that the graph is going to get to the x-intercept, but it's going to cross it. So that's the difference. This right here is touch and turn, and this one right here is cross. Now, what in the world is ET doing on this slide? Well, you don't have to learn it this way, but this is the way that helps me remember. So ET is what helps me remember when does a graph touch and when does it cross. So ET stands for even touch. So when you have an even multiplicity, the graph is going to touch, ET. And obviously, I don't know anything for OC, but the opposite of ET, right, is obviously the contrary. So if it's odd, it's going to cross. So that's, again, that's just a little thing on the side. You don't have to know that, but that's the way it helps me remember. So ET, even touch, and then obviously odd cross. Now, what in the world does this all mean? Well, let's go ahead and see if we could try this example here. So this one, we have an equation here. They're asking us to find the x-intercepts and the behavior at each. Lucky for us, this is already in factored form. So we already did an example of when it's not in factored form, you have to factor it out, but this one's already factored. So to find the x-intercepts, all I have to do is just grab this and set it equal to 0. If I set this equal to 0, let me do it up here. I set this equal to 0. I throw the 1 to that side, I get a positive 1. So I'm done. That's my x-intercept. Again, remember, x-intercept is the same thing as 0. Now, what's the multiplicity? Multiplicity is the exponent outside. So look at that. The multiplicity is 2. Now, they want me to find the behavior. Super simple. Remember, ETOC. If the multiplicity is even, which is this case, the graph is going to touch. So look at that. We already have one of our answers. Now we have to do that for every parenthesis. So let's do the next one. If I set this equal to 0, what answer do I get? I get 3. So I have an x-intercept of 3. Multiplicity of, there's no power here, so it's an invisible 1. So multiplicity of 1. And what happens when the multiplicity is odd? The graph crosses. Okay? Now, last one. Again, you don't stop until you're done with all your parentheses. So next parentheses, x plus 4. I set this equal to 0. If I throw the 4 to the other side, I get negative 4. Multiplicity is the exponent, so multiplicity of 3. And what happens when the multiplicity is odd? The graph crosses. So I think that was pretty simple, right? That's how you find your x-intercepts, and that's how you determine if the graph is going to touch or cross. Awesome. All right, let's try, and again, let me see, before we try another one, let me just show you what I mean, right? So look at that. We have an x-intercept here at negative 4, and look what the graph did. It crossed it. So that's how, that's what we figured out without graphing. Now, there's another x-intercept here, which is the 1, and look what the graph did. It touched it, and then it turned back. So we got this one right. And now the last x-intercept is right here on the 3, and look what the graph did. It crossed it. Okay, so I just wanted to show you what we're actually discovering. We were able to discover all of this without graphing it, but looking at the graph, this is what all the information means. All right, let's try another one. This one we actually had factored it out earlier, if I'm not mistaken. So this is the one we had factored out earlier. And then again, to find the behavior, all we have to do is just like what we did right now. So you would grab the first parenthesis, set it equal to 0. Grab the second parenthesis, set it equal to 0. Okay, so from here, all you have to do, right? So I set this equal to 0. Let me just go ahead and do it super tiny here. If I set this equal to 0, I throw the 2 to that side, it becomes a positive 2. And since the multiplicity is 1, that's odd. So that means it's going to cross. So that's how I got this answer. It crosses at 2. Now, the second parenthesis is this one. I also set it equal to 0. Now, if the 2 goes to that side, I get a negative 2. And we look at the multiplicity. Since the multiplicity is even, that means it's going to touch and turn at that answer. Okay, I'm hoping you guys are liking these. They're not that terrible. And that's the graph. So again, just to explain what this means, it touches, turns at negative 2. So look at that. It touches and turns at negative 2. And then at the positive 2, it crossed. All right, let's keep on going. Find all the x-intercepts and determine the behavior at each. So again, same thing, but look at this one. The reason I threw this one in here is because we have 2 parentheses, but we also have an x on the outside. You have to set all of them equal to 0. So if I set this equal to 0, which I'm going to do it over here, I have negative 2x squared, and I set it equal to 0. How do you solve this? Well, you divide both sides by negative 2. I'm left with x squared equals, and if I divide by negative 2, I have 0 divided by negative 2, which is 0. And then I do the square root of both sides, which I also get 0, right? The square root of 0 is 0. Now, I did this just so you would understand how I got this answer. But from now on, if you want to make a little note, every time you have an x in front of the parentheses, don't worry about solving it. The answer is always going to be 0, regardless. Whatever number you have here, whatever power you have here, because you always divide and you always do roots, but the roots of 0 is always going to be 0. So you could just skip that step. So I'm going to get 0. Now, what's the multiplicity? The multiplicity is 2. Okay. Now, again, if I set this equal to 0, I'm going to get the opposite, which is negative 7. Multiplicity, there's nothing, so it's an invisible 1. And then the very last one, if I set this equal to 0, the opposite is 5. And then multiplicity is the exponent, which is 3. Now, the last thing I have to do in order to find the behavior, I just look at the multiplicities. Are they even or odd? So super simple. Multiplicity of 2 is even, so that means here it's going to touch. Multiplicity of 1 is odd, so it's going to cross. Multiplicity 3 is odd, so it's also going to cross. So that's how I found my answer. The graph will touch and turn only at 0, and it will cross at both negative 7 and 5. All right, let's go ahead and do this example here. This one's going to have multiple parts. So let's go ahead and start by finding the graph's end behavior. Remember, when we're talking about end behavior, we have to use the leading coefficient test. We need 2 things. We need the degree and the leading coefficient. So The degree here is 5. Again, remember when we have parentheses, we add the exponent. So we have an exponent of 4 here. We have an exponent of 1 here, an invisible 1. So my degree is 5, which is odd. Now, we also have to look at the leading coefficient. Leading coefficient, remember, is 3 times the 1 times the 1, which is 3, and it's positive. Now, since we have an odd degree with a positive leading coefficient, the graph falls to the left and rises to the right. Again, I got that from the chart we had at the beginning. Let's go ahead and go to part B. Part B, find the x-intercepts and the graph's behavior at each. So there's no x in the front. I just get the opposite of this, which is -2 multiplicity 4. And I get the opposite of this, which is 3 multiplicity invisible 1. Now, touch or cross, we look at the multiplicity. Multiplicity of 4 is even, so it's going to touch. Remember, ET, even touch. Multiplicity of 1 is odd, so it's going to cross. Okay, so the graph will touch and turn at -2, but it's going to cross at 3. All right, part C, find the y-intercept. We don't have notes of this in this video, but we did cover it in a video from previously. So in order to find the y-intercept, all you're going to do is just replace the x's with 0. So I'm going to have 3 times 0 plus 2 to the 4th power, and then 0 minus 3. From here, you don't have to do any moving things around. You just have to compute. So 0 plus 2 is 2. And 0 minus 3 is -3. So I'm going to have 3 times 0 plus 2 is 2 to the 4th power times 0 minus 3 is -3. Now, if you compute this straight in your calculator, you will get -144. So just remember, just be careful you put this correct. It's going to be 2 to the 4th power times 3 times -3. Now, again, y-intercepts are written as ordered pairs, so here is my ordered pair, 0, -144. All right, for part D, we have to determine the maximum number of turning points. Now, if you remember from the second or third slide, to determine the maximum number of turning points, don't let it scare you. Remember, we use the formula. It's just a degree minus 1. So the degree for this problem was 5. 5 minus 1 is 4, so that means I have a maximum number of 4 turning points. So the graph should have max 4 turning points. Okay, I think that was pretty simple also. Okay, so I just wanted to walk you through the different steps that we've talked about with just a single example. Now, the last thing we're going to be talking about is creating an equation from a graph. So there's going to be some problems where you're going to be presented with a graph and you're going to have to come up with an equation. So this is what you're going to do. First thing you're going to do is you're going to use the x-intercepts to create factors. So we're going to have to find all the x-intercepts in the graph and write them down as factors. Step 2, we're going to ask ourselves, okay, is the graph touching or turning? And that's going to determine the multiplicity, because remember, multiplicities are even or odd depending on whether the graph touches or crosses. And then the very last thing we're going to do is we're going to use the leading coefficient test to determine if the leading coefficient must be positive or negative. Okay, this is going to be fun. We're just going to do 2 of these examples. So look at this. We have a graph, and we're going to have to find the actual function of it. So what we're going to do, step 1, we're going to have to find the x-intercepts. So I have an x-intercept of -2. So all you're going to do is create a factor. Remember, you do the opposite. So I'm going to have x plus 2. Okay, before I move on to the next one, what did the graph do here? So the graph touched it and it turned. So that means I'm supposed to have an even multiplicity. So you can use any even number you want. But since they're asking us to use the smallest exponents possible, what's the smallest even number you know? It could be 2, 4, 6, 8, but the smallest one is 2. Okay, so look at that. We have 1 down. Now, the next x-intercept is right here at 0. So I'm going to put x minus 0. Or you could do x plus 0. It's the same thing. Now, the graph, what happened? It crossed it. So remember, when it crosses, it's supposed to have an odd multiplicity. Odd numbers are 1, 3, 5, 7, but of course, the smallest odd number is 1. Now, let's keep on going. We have another x-intercept right here at number 3. So remember, you always do the opposite. It's a positive 3, so I'm going to have a negative 3. Now the multiplicity is, since the graph crossed, it's going to be an odd multiplicity. So again, odd numbers, but we're looking for the smallest one, which is 1. Okay, so here I actually did step 1 and step 2 in the same process, right? I found all the x-intercepts to create factors, and I found all the multiplicities. Now, step 3 is we have to use the end behavior of the graph to determine if the leading coefficient is 1 or -1. So up here in the front, I could have a positive or a negative number, but we're going to use the graph to determine that. So look at this. The graph is a crazy graph, but I just care at this. What's happening here? It's rising to the left, and then over here, what's happening? It's also rising to the right. So look at your chart. When does a graph rise to the left and rise to the right? That only happens when you have an odd degree. An even degree, right? Which we do in this case, 2 plus 1 plus 1 is 4. But it also happens when you have a positive leading coefficient. So the number in the front must be a positive one, not negative. Okay, so look at that. We created an equation. Now you're like, what in the world? That does not look like what we have, because we still have to simplify it. So x plus 2 squared cannot be simplified, so I leave it there. X minus 3 to the first power cannot be simplified, so I leave it there. But what is x minus 0? X minus 0 is just x. So that's why this little x came from. Okay, so that's all we have to do for these types of problems. Just to make sure it made sense, let's go ahead and do one more and then we'll wrap this up. So same thing, right? Let's go ahead and look at our x-intercepts. I have an x-intercept here that is at -4, so I do the opposite. It's going to be x plus 4. Since the graph touches and turns, it has to be an even degree. So I'm going to put it 2. Now the next x-intercept is right here. And this number right here is -2. So I do the opposite of -2. I do x plus 2. And now what did the graph do? Touch and turn or cross? It crossed it. So that means I have to have an odd degree. So I'm going to put a 1. Now the next x-intercept is right here. And that's at +1. So I'm going to do the opposite. I'm going to do x. The opposite of +1 is -1. Now, what did the graph do? Cross or touch? It crossed it. So I'm going to put a 1. Because remember, crossing means it has to be an odd number. Now, the last x-intercept is right here, which is at 1, 2, 3. So instead of a +3, remember, I do a -3. And now, did the graph touch or cross? The graph crossed, meaning it has to be an odd exponent, which is 1. So again, we did steps 1 and 2. Now step 3, we have to determine if the leading coefficient is 1 or -1. So what number goes up here, a +1 or a -1? So let's see. This graph keeps on going forever that way. So it's rising to the left. And then I follow the graph and it's actually falling to the right. So it's rising on the left and falling on the right. So go ahead and look at your table. When does a graph rise to the left and fall to the right? That only happens when you have an odd degree, which we have, right? 2, 3, 4, 5. So we have an odd degree. But what does your chart say? The leading coefficient has to be negative. So in order to fix this equation, I'm going to add a -1 in the very front. Again, it could be any number you want. It could be a -2, it could be a -5, it could be a -1,000. But since the instructions say to exclusively use a 1 or a -1, I use a -1. And then look at that, that's my answer, right? -1, which you don't have to write. X plus 4 squared, x minus 1 to the first power, you don't have to write it down. X plus 2, x minus 3.